Welcome to the Deep Dive, your shortcut to getting really well informed on the big topics. Today, we're jumping into modern data storage because let's face it, our data needs are just ballooning, right? And those older storage systems, they often can't keep up. So that's where these, software defined systems like Ceph come in. They're changing the game for how we store and protect data. Our mission here is simple: pull out the key insights from our sources on Ceph storage, focusing especially on its data protection method, Erasure Code. So by the end, you'll have a solid grasp on how these systems protect your data and, well, what makes them work.
Yeah, there's definitely a lot of buzz around solutions like Ceph. And for IT pros who are maybe more used to traditional setups, some of these features can be quite eye opening, especially around data safety and efficiency. It's a big shift.
A necessary one, it sounds like. Okay, so let's get practical. The question everyone managing data asks: a disk fails, it happens. How long does Ceph actually, take to recover? Are we talking hours, days?
That's a great question to start with. And yeah, it really shows a key difference from traditional RAID. With Ceph, the recovery time isn't just about the size of the failed disk. It's actually proportional to how much data was on that disk, the damaged data.
Ah, okay. So not the whole terabyte drive, just the actual files.
Exactly. Ceph only restores the affected data, and the really cool part is how it does it. It reheals that data onto healthy disks across the whole cluster,
Oh, interesting. So it spreads the load.
right? Which means basically the more disks and hosts you have in your cluster, the faster that recovery can potentially be. You could even tweak the speed using software settings.
Really? You can sped it up and slow it down?
Yeah, but there's a trade off, of course. Speeding it up uses more CPU and network bandwidth. So performance of your servers and your network definitely impacts the overall speed. And one other thing, replicated pools tend to recover faster than erasure coded ones.
Okay, that makes sense. So are there any like ballpark figures if I have NVMe SSDs versus older HDDs? And what about that flexibility you mentioned?
Yeah, the sources suggest for those fast NVMe drives, recovery might just take a few hours. For regular hard drives, maybe closer to a day, give or take.
A day. Okay, that's manageable.
And you hit on a key point: flexibility. Admins can totally throttle that recovery speed down. Maybe your application performance is critical right then, and you can afford a slightly slower rebuild. You reduce the resource hit.
So it's a balancing act then, speed versus system load.
Exactly. You're balancing how quickly you want that data fully protected again versus the immediate performance needs of your running applications.
That recovery aspect is really interesting. But you mentioned it depends on the protection method, and that often means erasure code in Ceph. This sounds kind of technical. What are these K and M numbers people talk about? How does that work?
Right, K and M. They're fundamental to erasure code. They basically define how data is split up and protected. K is the number of data chunks.
Data checks like
But
pieces of the original file.
precisely, when you write data, Ceph splits the object into K equal pieces, the data chunks. Then it uses math encoding to create M additional coding chunks from those data chunks.
Okay, K data pieces, M coding pieces. Then what?
Then, all those pieces, K plus M chunks in total, get scattered across what Ceph calls failure domains. Think of a failure domain as a boundary for failure tolerance. It could be a single disk, maybe a whole server host.
Or even bigger, like a whole rack.
Exactly. In big setups, it could be a rack, a server room, even a whole data center. The crucial part is that Ceph spreads these K plus M chunks across these domains. And the magic is you could lose up to M of those failure domains simultaneously, and your data is still safe. You could reconstruct it from the remaining chunks.
Wow, losing M whole servers or racks. That sounds pretty resilient. But there's always a catch, right? What's the impact on performance? And maybe more importantly, how much storage space do I actually get to use?
That's the core trade off, you're right. Compared to just making multiple copies, replication erasure coding usually gives you much better space efficiency. You waste less raw disk space.
Better space efficiency. Okay, less wasted space. Good.
But the flip side is performance, especially for IOPS heavy workloads. Think databases, lots of small reads and writes. Erasure coding generally involves more disk I/O operations for reads and writes because it might need to read multiple chunks and do calculations to reconstruct data.
So maybe not ideal for everything.
It depends. And actually, the size of K and M matters too. A larger K plus M total means more disk operations, potentially lower IOPS. However, if you have large files like video or backups, using a bigger K and a smaller M can sometimes improve throughput because you're transferring less total data across a network for the coding part.
Interesting nuance there. So let's get back to space efficiency. If I use K and M, how do I figure out, the percentage of my raw disk space I can actually store data on?
It's actually a really simple formula. Your usable space efficiency is just K divided by K plus M.
K divided by the total number of chunks.
Exactly. So a common example is K4 M through 2. That means 4 data chunks, 2 coding chunks. Your efficiency is 4 divided by 4 plus 2, which is 46, or about 66.7%.
Okay, 66.7%. How does that compare?
Well, compare that to standard triple replication, which is replica 3.
Yeah,
That only gives you 13 efficiency, or 33.3%. So K4 M2 is literally twice as space efficient.
twice the usable space.
Mm.
But you said replica 3 might be better for IOPS?
Generally, yes, replication is simpler and often faster for high IOPS needs. With erasure coding, for good space efficiency, you typically want K to be larger than M. And the bigger the difference between K and M, the more space you save. It's a knob you can turn.
Okay, understanding K and M is one thing, but this has real hardware implications, doesn't it? How many physical servers, OSD hosts, do I actually need to make an erasure code pool work properly?
It does, absolutely.
Yeah.
The sum K plus M directly influences the minimum number of failure domains and thus usually hosts you need. Best practice is really to set your failure domain to host or even rack.
Why not just disk, like an old RAID array?
You can set it to disk, which protects against simultaneous disk failures within potentially the same host. But setting it to host means chunks are spread across different physical machines. If one whole server goes down, the chunks needed for recovery are already on other healthy servers. It makes recovery much smoother.
Makes sense. So, what are the recommendations for minimum host counts based on K and M?
Right, there are sort of 3 tiers our sources point to. The best setup is having your number of servers be at least K plus M plus 1.
K plus M plus 1 extra.
Yep. That way, every single chunk, K plus M of them, can land on a different host. And crucially, if one host fails, you still have that extra, the plus 1 healthy host, available immediately for Ceph to start rebuilding the lost chunk onto. No waiting, maximum resilience.
Okay, that's a gold standard. What's next best?
The second best is having exactly K plus M servers. Again, each chunk can be on a different host, which is great for initial fault tolerance.
Yeah.
But if a host fails now, you've lost one of your K plus M locations, and there's no spare host ready to take over that chunk immediately.
Ah, so the system is degraded until you fix or replace the failed host.
Exactly. You've lost your redundancy for that data until the repair happens.
Mm.
Prompt action becomes really critical.
And if the budget is tight, is there a bare minimum?
Yes, there's a budget limited option.
Yeah.
You can get away with having the number of servers be greater than or equal to K plus M divided by M.
Okay, K plus M divided by M. Let's use that K4 M2 example again. That's 4 plus 2, 2 equal 3 hosts minimum.
Correct. Just 3 hosts for a 4 plus 2 EC pool. Now, this setup will protect you against certain failures like multiple disks failing in just one host, or losing one entire host, or even one disk failing in each of up to M hosts simultaneously.
That still sounds quite robust for just 3 hosts. What's the catch?
The catch is similar to the K plus M scenario, but potentially worse. If you lose one host in this minimal setup, you often don't have enough remaining healthy hosts for Ceph to automatically reconstruct and reheal the lost chunks onto. You're relying heavily on getting that failed host back online quickly.
Wow, okay. So that choice of server count isn't trivial. It's really about cost versus redundancy level versus how quickly you need automatic recovery versus manual intervention.
Precisely. It's about designing for your specific risk tolerance and operational capabilities. Critical decision.
Definitely. So moving from protection to actual usage. Perennial question. How much storage space do I really get? How do we calculate the usable capacity of a whole Ceph cluster?
Right. Calculating the final usable number involves a few steps. First, you obviously need your raw capacity. Just sum up the total disk space from all the drives and all your servers.
Simple enough, add up all the terabytes.
Yeah, but remember, if you have different types of drives, like fast SSDs for some things and big HDDs for others, you should probably calculate their raw capacity separately. Ceph can handle different device classes.
Okay, raw capacity first,
Then, data protection overhead. This depends on the pool type. For your replicated pools, the usable space is just the raw capacity divided by the replica size, usually 3, so raw divided by 3.
Got it. And for erasure code pools,
For EC pools, it's the raw capacity multiplied by that efficiency factor we talked about, K plus M.
raw times K over K plus M. Okay.
Is that it? Almost. There's also a bit of system overhead. Ceph needs some space for its own metadata journaling internal operations. This is usually estimated at around, say, 10 to 20% of the raw capacity. It varies a bit depending on configuration.
So raw capacity minus protection overhead minus system overhead. gives me the usable space.
Broadly, yes.
Yeah.
Though it's a bit more nuanced because of how Ceph pools space.
Ah, right. You mentioned something interesting earlier. All the disk's space is shared.
Hmm.
And something about thin provisioning. What does that mean for me?
Yes, that's a key Ceph benefit. Unlike some systems where you dedicate specific drives to specific tasks, all the storage drives contribute to a central pool of raw capacity. Then your replicated pools and your erasure code pools draw from that shared capacity.
So I don't have to pre-allocate drives for specific pools?
Nope. And thin provisioning builds on that. When you define a pool or set a quota, Ceph doesn't immediately reserve all that space. Space is only physically allocated from the shared pool as data is actually written.
Oh, that sounds way more efficient.
It is. It massively improves utilization because you're not sitting on large chunks of pre-allocated but empty space. It helps reduce costs significantly.
Any best practices around managing that shared pool?
Yeah, one common recommendation is to try and keep about one of your total space free during normal operation, where n is your number of servers. This gives Ceph breathing room for data rebalancing, and crucially, for recovery if a host fails.
Leave some buffer space. Makes sense. Does Ceph warn you if you're getting full?
It does. There are preset thresholds. Typically, you get a near full warning around 85% capacity utilization, and a full warning where things might start to slow down or block writes around 95%. Helps you stay ahead of capacity issues.
Okay, fantastic. So let's recap this deep dive. We've covered how Ceph recovers from failures focusing on damaged data, leveraging the whole cluster. We've demystified Erasure Code's K&M numbers and their impact on space and performance. We looked at how K plus M dictates minimum server counts, balancing cost and resilience. And finally, how to calculate that all-important usable capacity, considering raw space, protection, overhead, and features like thin provisioning. The big takeaway, really, seems to be that understanding these details gives you the power to make much smarter choices about designing and managing your storage infrastructure. You can tailor it to exactly what you need.
Absolutely. And maybe a final thought to leave you with. Now that you have this deeper understanding of how Ceph's erasure code works, with its different configurations and trade-offs, how might that change how you think about balancing storage cost, your specific performance needs, and what level of risk or recovery scenario you're truly comfortable planning for?
That's a great question. Food for thought.
It pushes beyond just the specs and into operational strategy. How does this capability potentially influence your next infrastructure decisions or even your disaster recovery planning? It's worth pondering. Thank you for watching our videos. Hope you learned more about Ceph. Please leave a like, subscribe, and share this video. We will see you next time.